Salutations, everyone. Kickstarting our webinars this year is our Vessel Performance Info webinar, Simulation to Help Manage LNG Carrier Boil-Off Gas, from our sponsors, Danelec. Joining us today is Danelec's Product Manager in LNG, Konrad O'Sullivan. If you have any questions, there's a Q&A section for you to type them in and leave an upvote. And here's Carl Jeffrey, founding editor of Digital Ship and our main host. Over to you, Carl.
So we're going to talk today about how we can use digital simulation tools to manage boil-off gas on LNG carriers. So that's the small amount of liquefied gas that evaporates during the voyage. It's a complex challenge to manage because the composition of boil-off gas changes during the voyage. For example, if the LNG is richer in nitrogen at the start of the voyage and the nitrogen boils off first, then the remaining cargo has a different composition. And we have to manage boil-off gas to make sure the vessel arrives at the discharge port with temperature and pressure below the specified level. And we hear that vessels sometimes have to sail around in circles until their cargo reaches the required temperature and pressure for discharge. So to make it all work, crew have to make complex operational decisions, and any changes they make can affect the cargo pressure, the cargo temperature, and the rate of change of composition. But we can use digital simulation tools to help us, making predictions in advance and supporting our decision making. They can make recommendations for the best way to meet different objectives, whether that's avoiding delays or maximizing LNG delivery, minimizing fuel costs, or minimizing emissions. And we're going to hear today from Konrad O'Sullivan. He's lead product development manager at Danelec, where he focuses on LNG carrier voyage simulation and optimization. He's joining us from New York. He's a naval architect and marine engineer, and also spent time working in shipyards. And he's got onboard experience sailing on board the Maersk Piri tanker and other tankers. We're going to have a talk from Konrad of about 25 minutes, including a demonstration of the software. Then we'll take your questions. And I'd like to invite Konrad to start his talk.
Excellent. Thank you, Carl. And let me get going and share my screen.
Yeah.
Okay. Carl, able to see this? Are we coming?
Yep.
coming?
Oh, good. Yep.
Beautiful. All right. Well, welcome everybody. Today I'll be talking about simulation to help manage LNG carrier boil-off gas. Our simulation tool set, where we are simulating LNG carrier voyages for a slew of reasons. I'm going to get really deep into it, but before I do, let me talk about Danelec for a second. So just spending a couple minutes here. Danelec at a glance, we are a leader in maritime data collection, safety, AI analytics, both on board and on shore. We've spent over 30 years in the market and have a large install base, over 14,000 vessels, a large partner network that we leverage with over 200 partners, and we are one of the industry leaders in high-frequency data collection, with this past year collecting over 1.5 terabytes of data. Also, we have a global network of over 700 certified technicians delivering our service to vessels across the world. The LNG boil-off simulation that I'll be talking about today is just a small part of this. And really quickly about the broader ecosystem that the LNG simulation sits within. So Danelec, and by the way, can you guys see my my mouse on screen, Carl?
Yes, I can. Yeah. Beautiful.
So Danelec, beyond the LNG capabilities, like I said, we are leaders in high-frequency data capture via our VDR. We also have Kima power meters that are well-known in the industry. And with the data flowing from our VDR, from the Kima power meters, we can connect to our onshore solutions via API, but we also have onboard solutions where the crew is our key stakeholder, where through our Danelec Onboard Insights platform, Danelec Edge, and Danelec Connect, the crew have the ability to monitor performance and make operational decisions. And lastly, our onshore solution ecosystem consists of fleet insights, voyage insights, of which the LNG simulation is a part of, as well as safety insights. So as a whole, we are an end-to-end solution, an entire ecosystem bringing value for performance monitoring, vessel and voyage optimization, and data collection. Okay, that context out of the way, let's dive into the meat and potatoes. simulation to help manage LNG carrier boil-off gas. So first off, let's talk a little bit about why the LNG segment is a bit unique compared to other segments and some of the challenges. So LNG carriers are very unique in that they are actually using their cargo as fuel. And not only that, that cargo is itself dynamic over the course of the voyage. The composition is changing, the energy density is changing as a function of how long the cargo is sitting in the tank, the weather the vessel is experiencing, how much sloshing occurs in the tank. That's affecting the pressure of the cargo, the temperature, and the composition. And we refer to this as aging, where the cargo tends to boil off nitrogen early in the beginning of a voyage, and the relative amount of methane, other higher alkanes, is increasing over the voyage, increasing energy density. It's also very important to maintain strict temperature and pressure conditions within the tank. We don't want the tanks to explode, obviously, so we need to stay beneath minimum pressures. So it's important to condition the cargo over the course of the voyage so that we are meeting those safety standards. But additionally, cargoes delivered at the end of the voyage are required to meet set terminal arrival pressures and temperatures. So over the course of the voyage, we need to maintain our cargo in such a condition that we are, one, operating the voyage efficiently, but also meeting our arrival pressure and temperature requirements. Now, operators have to continuously adjust the myriad systems they are working with in order to make sure that this cargo condition at arrival is maintained, while also trying to make the voyage as efficient as possible. So it's really a complex balancing act where we have weather, we have cargo conditions, we have the LNG loaded cargo condition at the time of loading. We have these propulsion and cargo systems that we can play with to determine when we're going to get to port, how are we going to make sure that our pressure and temperature stay within limits, and we have these terminal and charter party requirements. So we have all of these factors that are playing in, making performance prediction and operation of the vessel a complex challenge. It's not straightforward. We have a lot of variables to play with. Now, diving in a little bit deeper into the technical challenge here, we have all these levers that we can pull, and we're still trying to minimize total LNG consumption. That way we can maximize the total cargo we're going to deliver at the end of the voyage. So like I said, we need to balance temperature, pressure, our ETA, making sure we get to port on time, but we have all of these different levers to play with. We can adjust our speed, we can adjust our engine mode, how much gas versus fuel oil is being fed to our main engines. There are many different propulsion system types, different main engine types with their own different constraints. We can employ reliquefaction or subcooling, of which there's also many types, full reliquefaction systems, partial, different subcooling systems. So how exactly we operate those to condition our cargo isn't exactly obvious in conjunction with all of the rest. We can play around with our route, weather optimization to avoid bad weather, to increase our overall or decrease our overall fuel consumption. But also there's the impact of sloshing on the cargo. As we hit waves, our cargo is going to slosh around, and that's going to impact the pressure of the cargo over time. And lastly, GCU use. That stands for gas combustion unit. Do we need to burn off additional gas? And when should we do that over the course of the voyage if we want to keep pressure down, but still maximizing LNG cargo delivery, minimizing that total consumption? So there's all these different levers to pull that we can adjust in order to meet these arrival requirements. And it's not exactly clear what is the best way to do those to ensure that we're maximizing delivery. So what are the key challenges to the segment as a whole, given all of those technical challenges? Well, first off, we have a lack of prediction performance tools because of the myriad because of the complexity of all these systems that I just talked about. There's few overall performance and prediction tools that take all of them into account and can accurately predict how a cargo condition is going to develop and how the performance of the vessel and voyage will be over the course of that voyage. We have, and this leads to operational inefficiencies. Because it's not exactly clear and straightforward how we should operate this vessel, we know we're leaving some money on the table in terms of the way we're actually operating the vessel. Beyond that, we have siloed decision-making, where different users are using siloed data sets. We have technical teams, operational teams, commercial teams. They're all making decisions at different part in the voyage planning stage, different parts of the voyage planning stages that all affect the overall outcome of the voyage. For example, if we're setting an ETA very early in the planning stages, but the requirements for the voyage and the cargo conditioning requirements don't quite align with that maybe too early or too late ETA, we could be leaving some money on the table in terms of how much cargo conditioning is required to meet terminal requirements at a certain ETA. And if that was adjusted, could we have a better voyage outcome? So all of these things are leading to overconsumption, reduced cargo delivery, and increased emissions. And at the end of the day, we're leaving money on the table when we're running these LNG carrier voyages, and they could be more efficient. We could be delivering more cargo. So what is Danelec's solution for you? Danelec developed an advanced platform that empowers users to simulate LNG carrier voyages. Not only just the voyage, the propulsion systems, the conditioning systems, but also the actual condition of the cargo over the voyage, including temperature, pressure, as well as the composition over the voyage, which is very important considering that the quality of the LNG loaded can vary significantly depending on where you pick it up. For example, cargoes picked up at Freeport, say, have a very high nitrogen content, which has significant impacts on the overall consumption over the course of the voyage, the energy density specifically at the onset of the voyage. So with these simulation tools, we're able to simulate vessel performance, precisely voyage outcomes, so that charterers, owners, operators can make better planning decisions, execution decisions, and realize more LNG delivered at arrival. Now, how do we do this? We have two sort of distinct flavors that I'll get into, but we have simulation of operational set points and optimization of set points. So with simulation tools, we are able to simulate a voyage plan. We know we want to do X, Y, Z in terms of our propulsion system, our cargo conditioning systems, and if we our route, and if we simulate exactly those set points, we're able to predict what are the key outcomes of performance and cargo condition throughout the voyage and at arrival. But users might also want to ask the question, okay, I have specific requirements that I need to meet. How do I best get to those requirements while minimizing consumption? Well, for that, we have optimization of set points, where given requirements, we can with simulation tooling, spit out exactly what the best set points in terms of conditioning systems, how fast should I go, how much relix should I use GCU? What are the best set points that I should employ to minimize LNG consumption? And how do we do this? Well, this is a data science enabled effort. We use a series of models, machine learning models based on high frequency data coming off of the vessel that we collect to predict heat ingress into the tank, the amount of evaporative cooling that's going to occur due to the boil off of the liquid into the vapor phase. We model the actual cargo condition in terms of the vapor temperature, vapor pressure, the composition of the cargo over the course of the voyage, how much the LNG is heating up due to the heat ingress into the tank. And we're also modeling the actual vessel systems, propulsion systems. How fast will the vessel go in a certain sea state along a certain route with contextualized by wind, current, wave height? How much fuel is the vessel going to consume given a certain power, given a certain energy density of the LNG? And cargo conditioning systems performance. Given the certain reliquefaction system, for example, you might have on board, how much reliquefaction do we expect to produce given a certain compressor power, say, or power input into that system? And really quick, here's an example of that. So we take a myriad of tags off of the vessel. We do what we call feature engineering, where we're looking at exactly what are the most important tags that can be used as predictors for a certain target variable. We carefully filter that data, where we remove outliers. We consider conditions that are most important when we want to model certain systems in certain conditions. And then using all that, we train our models to predict certain features with the context of other data feeding into those models. Now, up here on the top right, we see an example of the results of a vapor pressure prediction model, where the red line is our prediction based on the model, and these black dots are what was actually observed. So here we can see quite close alignment, where we are not using this observed data within our model prediction. We have a separate training set, and then we will predict, in this case, vapor pressure without using this exact data within. Now, an example that's a bit clearer to see, here we see some actual cargo condition prediction results for a 12-day LNG carrier voyage, where these black lines represent the actually observed temperature on the left and actually observed pressure here on the right. And the red lines represents our modeled predictions. On average, we're seeing over 14-day voyages, root mean square error of less than 1 kPa for our pressure prediction, and I believe it's about 0.05 degrees Celsius temperature root mean square error. So we're seeing very, very good results over the course of these voyages, which lend a lot of confidence into the results that we're predicting, say 14 days out, 21 days out for these longer voyages. It's this sort of data that gives us confidence that we're able to make optimization predictions early in the voyage that will actually bear out when we're prescribing, say, an optimization recommendation, that if you do X, Y, Z, this is what's going to occur. All right, with that, let's jump into what this tool actually looks like. Bear with me for a second as I bring this up. Okay. Now here we've landed into the tool, our boil-off optimization tool. This is an online web portal that users can log in onshore, on board, and simulate their voyages or get prescribed optimal recommended set points for a specific voyage. So what we're looking at here are time series, in this case of speed over ground and LNG consumption over the course of a voyage from Barrow Island to Zhuhai. Now, this red line that you see, the solid red line, is actual data that we've observed coming from the vessel over the course of the voyage. And this dotted line represents our prediction into the future. Like I said before, this prediction is based on the weather we forecast along a specific route, including wind, wave, and current, the angle of incidence the vessel's experiencing, all of those things. And as we move along the trace, we can see in high resolution what the values are. Now, we have these prediction plots for average speed over ground, total LNG consumption, and also fuel oil consumption. We are also considering pilot fuel, and we're able to simulate any engine mode, full gas, full fuel oil mode, or something in between, depending on what engine system is installed aboard your vessel. And let me pause and say it's also important to note, all of the models we're creating are bespoke to each unique vessel. So there's not a single set of models that describe all LNG carriers, say your typical large LNG carrier, a Q-Flex, for example. No, rather each model is tailored to a specific vessel that is populated with that vessel's data. So beyond predictions of speed over ground, LNG consumption, rather total propulsive fuel consumption, which are pretty standard, we also show predictions of cargo condition. So given the amount of LNG consumption we expect to meet a certain shaft speed or meet a certain speed over ground, how much reliquefaction or subcooling we're predicting, as well as the weather the vessel's experiencing along a route, we're also predicting how the cargo condition is going to change over the course of that route. So in this plot, we are showing the predicted cargo pressure and predicted cargo temperature as a function of all those other features over the course of the entire voyage and into the future to arrival. Beyond temperature and pressure, we also predict methane, or rather cargo composition, in both the liquid and vapor phases as the voyage develops. So that includes methane, nitrogen, ethane, the higher alkanes in both the liquid and vapor phases. Now, this information is really important for onboard users who might want to know when does the nitrogen content in the vapor phase drop below a certain level, so I can avoid risks like knocking in my main engines. Or how much total nitrogen, say, did I boil off over the course of this whole voyage? As at the end of a voyage from Freeport, for example, maybe being claimed for overconsumption. And then I can see exactly how much of my total cargo was lost totally due to nitrogen and not, say, inefficiency in operating the vessel. Moving along, we predict cargo systems. Here we're showing reliquefaction. In this demo, there's no reliquefaction system aboard this vessel, so we're predicting no reliquefaction. In this case, we decided to simulate a set amount of subcooler cooling power. So we're predicting 175 kilowatts of subcooling throughout the course of the voyage and GCU consumption. In this case, we're prescribing no GCU consumption. But if we were, all those values would show up here. And lastly, like I said, all of these features are contextualized by the weather the vessel is experiencing along the route. And here we can see our weather forecast of predicted wave height, wind speed, and sea current over the voyage. So all of these plots are intended to give a really high resolution view of what we can expect given a voyage plan that I've set up or recommended set points that the tool is suggesting that you do. Now, really quick, up here on the left, here's where we see some interesting high-level metrics pertaining to the simulated voyage. We see where the vessel is coming from, where she's going, what my total distance is for the route that we've entered, what is the total duration given the shaft speed that we're simulating, what is the cargo temperature and pressure at arrival, and how much LNG am I going to be able to deliver once I arrive. So high-level information for users so that they can quickly answer questions about how much cargo am I going to be able to deliver, and will I meet my required terminal arrival requirements of pressure and temperature. But beyond that, we have a few more sections here that I'll expand. So recommended set points. If a user came and put in a specific temperature and pressure that they needed to hit at arrival, this simulation tool will spit out exactly how we think the vessel should operate to minimize LNG consumption while meeting those requirements. In this case, a shaft speed of 52, fuel modes, that is ratios of the LNG consumption to fuel oil consumption for the different engine consumers, the main engines and the generators. How much subcooling, cooling power should I do? Reliquefaction, GCU. So this is trying to answer the question, how should I operate my vessel from an onboard perspective? And lastly, we see some summaries of the overall voyage metrics. What was my average speed over ground for the voyage? What was my total LNG consumption, total GCU, total subcooling? So we have high-level aggregates of vessel performance here for interested technical users. Now, how are we leveraging this tool? Well, for different users, this can be leveraged in different ways. For onboard users who want to know what is the best way to operate my vessel, we can prescribe recommended set points. Now, for planning purposes, for the captain before departure, for the charter trying to set voyage instructions, a user can simulate a voyage from here to there before the vessel actually departed and get an idea of how much consumption is actually going to occur. What amount of cargo conditioning is going to be required to meet my arrival requirements? What is the benefit of taking this route versus that route? And how will that affect my overall vessel efficiency, voyage performance, and total consumption at the end of the day? And also at the highest level, where should I deliver my cargo, or which vessel should I utilize? Users can simulate different voyage plans and even different vessels going to different places. And with information about how much total LNG is delivered, what are my cargo conditioning requirements, those users can make choices about maybe it's more smart to utilize this vessel on this route, or maybe I should choose a different vessel or choose a different route or a different discharge port. That way, at the end of the day, I am maximizing my efficiency, maximizing profitability, and the total amount of LNG cargo delivered. But beyond a heavy technical tool, we also really want to lean into collaboration across the charter party, because that's where we see a lot of inefficiency. In support of that, we developed the simulation history database. So any user can come in, simulate a voyage, a leg on that voyage, and share and collaborate with whoever they want. So here we see a database of past simulations that we ran for this vessel, for this voyage. Now, any user can come in here and quickly share these results with the high-level metrics clearly shown with different team members, with the folks on board, with the folks on shore, to the charterers, to the owners, so that everyone is working with the same data, the same results, so that we can make more informed decisions to enable better planning, better voyage execution, and maximizing delivery. And really quick, because I know I'm coming up on time, how does a user set up a voyage like this? Well, first off, a user comes in and specifies a leg that they want to simulate, and a user can input any route. Now, we know weather optimization providers will be sending updated route recommendations constantly, so my route might constantly be changing, or we might divert to a different discharge port. And at any time over the voyage, a user can come in and specify a different route, quickly inputting an RTZ file or directly entering waypoints. And then users are able to simply input the requirements for those voyages. So users are prompted to input a required arrival pressure, temperature, ETA, and then some information from the certificate of quality. What is the actual quality of the cargo that I loaded on board? And with this information alone, a user can hit submit and then get spit out all of the recommended set points and what are the voyage outcomes for my voyage going to be, given these requirements. We will recommend set points that are going to minimize total LNG consumption. However, a more savvy technical user can come and play around with very specific set points. A user can come in here and fully describe a voyage plan, entering the reliquefaction rate or subcooling rate they wish to operate with, their shaft speed, boiler consumption, generator consumption, engine mode, and fully define a voyage plan so that we can answer the question, what will happen if I operate with this voyage plan as opposed to that voyage plan? So a lot of capabilities here to support what-if scenarios. All right. And with that, I'm going to jump back into the presentation very briefly and talk about what sort of value is this bringing to our users. So on average, we're seeing about 35 metric tons of LNG savings captured by users of these simulation tools per laden leg. Now that's being realized by slowdown for just-in-time arrival, minimizing total propulsive consumption, maximizing reliquefaction, which is particularly interesting for vessels with partial reliquefaction systems, and optimization of that engine fuel oil to gas ratio. For example, we often see cases where a vessel is utilizing their GCU late in the voyage. However, they were operating on a fuel mode for most of the voyage, where they could have, instead of just burning that GCU late, they could have optimized and used it for propulsive consumption early, minimizing the LNG they'd have to consume. But a key use case we also see, beyond the actual operators, owners, charterers, is negotiating with terminals. When we have all of this high fidelity, highly accurate simulation results for overall voyages, and we have a picture of what the total amount of cargo conditioning that would be required to meet terminal requirements is going to be, we've seen users use those results, take them to the LNG terminals, and negotiate for a less onerous arrival pressure. So let's say a vessel has to come in at 12 kPa, for example, and it's going to take an arm and a leg to get our cargo down to that pressure. Well, with accurate simulation results, our users have been able to negotiate and actually realize savings by raising the terminal pressures that they're going to come in at. And we see about 50 metric tons per LNG per kPa of pressure rise realized by our customers. So all of that adds up to, on average, about $150,000 in total savings per vessel per year. So really great stuff. We see a ton of operational inefficiency out there in LNG operations right now. Like I said, because the folks who are planning and executing, they're using different data sets, silo data sets. They're making silo decisions. They're not talking, collaborating, using a similar understanding of vessel performance and voyage outcomes. And all of that is leaving money on the table that tools like this seek to get back. All right, Carl, I think that was a about my allotted time.
Well, thank you very much. Okay, so we'll go into questions. I can see. Oh, there we go. We've got a lovely question to start off with. Charles Alexis Demien is asking how many vessels are using this. Is that commercially sensitive question or something you want to answer? Or
That's it's a little commercially sensitive,
feel
but
free to ignore it if you don't want to take
I'll
it
answer it. I'll answer it.
off.
We have experience using this tool aboard Meggies, XDFs, fuel oil only vessels with full relic systems, DFDEs, full relic systems, partial relic systems, subcooling systems. So virtually every vessel type that's out there, we've experienced creating models for and running simulations for.
Yeah, that's very good. Yeah, if you want to stop screen sharing, then people can see us with better.
Sure.
Yeah. So what's the alternative to using this? I mean, that's so I mean, I imagine every ship would have this, but I don't know anything about what LNG ships simulate and don't simulate. Is it I guess don't you have any simulation at all? It's all done by trial and error if they don't use a thing like that, is it?
So today, in our experience, we see everyone from the largest energy majors to the smaller LNG shipping companies relying on experience, heuristics, rule of thumbs, and Excel spreadsheets. Now, not saying that those are invaluable. The experience and the results predicted by those spreadsheets definitely valuable, but they're not predicting with the accuracy, with the high fidelity that simulation tools like this are able to predict. There's certain assumptions baked into the ways that we're estimating performance today that aren't picking up the nuances of, say, sailing to this weather or using this certain system, which has its own performance characteristics, maybe that are dynamic in time, as a reliquefaction system loses efficiency, for example. So while the experience and while those tools are good, they're not capturing quite the full picture.
Oh, yeah. We imagine in the future everything's going to be simulated like this, and we'll have a full granular view of what's going to happen. And this is the sort of world where we're going towards, isn't it? I think. And yeah. And then the kind of data setup. So I don't even know if you can tell the composition of a cargo in an LNG carrier. Is there a sensor, or do you have to put it into some chromatograph or something to understand it? They have sensors that read it the whole time, is it?
Well, I can talk a little bit about the data set for something like this, and in the certificate of quality data. So every time an LNG carrier is loaded, a certificate of quality is generated that talks about the molar composition of methane, ethane, nitrogen, all the components of LNG. And that's fed into our simulation tool for a highly accurate prediction. But say you're doing a pre-voyage planning or something like that, you might not always have that information on hand. So what we've done is actually developed a database of typical certificates of quality, typical compositions coming out of different terminals from around the world. And that information can be leveraged to say, okay, I don't have exactly my COQ for this particular voyage, but I know close enough about what the quality of my LNG is going to be so that we can make a simulation. And now those might be dynamic in time coming from certain terminals, but it definitely gets us there and helps us with our prediction.
Oh, very good. So we've got another question from Charles Alexis. I've just looked you up on LinkedIn. I see you're an AI engineer with OSE Engineering in Paris, but he's asking how many months does it take before having a good model? Yeah.
Great question. So in order to develop a model that's of sufficient quality for us, where we're seeing predictions, like I said, of about less than 1 kPa root mean square error, we need about 3 months or about 3 laden legs worth of data. Now that data doesn't have to. If we start collecting data, it doesn't mean we have to hook up the pipes and then collect data for 3 months. If vessels have historical data collected sitting in a database somewhere, which they almost always do, a model can be generated in a matter of days. With robust data science modeling pipelines that we have at Danelec, it's just a matter of making sure we have the right features and then creating the data. So for simulating these laden legs, about 3 laden legs worth of data, and then we're getting good results. And I do want to call out one of the benefits of simulation using this approach as opposed to a first principles approach. So feeding into these simulations, we are not, say, modeling the geometry of tanks. We're not looking at a GA and considering heat flux through large planes. This is all based on purely data feeds. So just with the information about the weather outside, the systems that are running, how much consumption is occurring, reliquefaction, we are able to build up models of thermal conductance, of the evaporative cooling effect of boiling off the cargo. So that method really cuts down on the time it's required to create models, losing the first principles approach there.
Oh, so do you call it AI, or simulation model is something a bit different, is it? Or I guess you could call it AI if you wanted to.
You can consider this digital twin modeling. So
Right,
it's
yeah.
We have a collection of data science powered models, machine learning powered models that are being used to create this overall simulation. And they're constrained by key naval architecture principles, not just black box models, but rather features, a bunch of features that are being used to predict a target constrained by what we know from the laws of physics.
It's real world simulation then. Yeah. Yeah, you can see how it actually works and how it's calculating it, and yeah. Oh, nice. And where did it come from? So, I mean, I only heard about this when I met you at SMM, but is it something you've been developing for many years, or is it? I mean, it must take quite a long time to build something like this, isn't it?
So this had its origin now maybe 4 or 5 years ago, back with Nautilus Labs, that was acquired by Danelec. Back then, we were trying to help energy majors answer some of the questions they had about operating LNG operations for a particular vessel, or answering a very specific question about how should I be operating this vessel with a PRS system in certain set points. So that evolved so answering that question turned into an exercise where we were modeling the pressure and temperature of the tank, modeling the compositional change over time, which then itself developed into a recommendation service, where for certain vessels, we were simulating voyages on a daily basis, updating it very akin to weather routing optimization, and on a daily basis, pushing out recommendations to vessels for this service, updated day over day over day. Now, after a lot of time doing that, we gained some experience and realized users want the ability to come in. You guys are the experts, the LNG operators and charterers. They wanted to come in, play around with the models, do what-if analysis, test out different scenarios, check out the models themselves. So that was the impetus for creating this simulation tool set, where we're giving users full control over simulation of their voyages and optimization and prescription of recommendations.
Wow, so it's originally a kind of remote expertise thing, but now it's something people can do themselves. Yeah.
So yeah, this was definitely built with key players out there in the industry. Close collaboration with the folks on board the ships, with the folks running these ships, that all fed into the development of this product as we captured the experience and expertise of the guys actually running these vessels. We're trying to best answer those problems: the charters, the owners, the planners, the executors, trying to keep them in mind as we develop this to bring the most value to our clients.
Oh, very good. I've got a question here from Philip Jones. There's a Philip Jones I know who works at BP as vessel operations manager, so perhaps we'll take that first if that's him. He's asking, can you model Frankenstein cargoes, which might have a large heel in one tank, another tank with high nitrogen, and 2 other tanks with a lean cargo, such as Trinidad up? You probably know what the phrase Frankenstein cargoes means. I don't know myself.
That's a good question. Right now, our simulation only considers homogeneous cargoes, similar loading. So, and actually, we've I'm not sure if we've tried to model Frankenstein cargoes before, but that's a great use case. It's a little bit more of an edge one. So, in terms of our product development, we've prioritized getting other features out there or other simulation capabilities. But great question, and something we're thinking about as it comes up.
He's talking about the tanks on the same ship being different. I think that's what that's another level of simulation. I'm sure it's possible to do technically, but yeah, so another level. Yeah. And then so Divya Iyer, who's with ABS Wavesides in the US, asking about the source data for training the model. Is it sensor data or vessel reports or design documents? Is that I think
so two of the three. So this is all based on high frequency data coming from the vessel. as well as some design documents. For example, knowing the capacities of certain systems. What is my maximum, I don't know, GCU capacity, minimum capacities there. Knowing information about the tank sizes, the actual volumes, some information about piping volume here and there. So a little bit of design documents, but like I said, we're not doing a full first principles geometric model of the vessel. We just need a few vessel characteristics and systems characteristics. And then we're just leveraging high frequency data coming from the vessel. This can't, and we've played around with trying this using noon only data, but to capture the high resolution changes in temperature and pressure that occur within the duration of one day, noon data is a bit too sparse to enable the prediction accuracy. We're not getting great results using just noon data. So high frequency data.
Oh, very good. So we're going to Sweden now. Lennart Cederberg, who's a meteorologist in Norcare. He's asking, it's a bit complicated. So we're talking about the sea package, but there's also boil off when the cargo has arrived in the terminal. Are we also going to simulate what's optimal all the way to the final consumption? I think no, that's the answer to that. We're just optimizing to the. Oh.
Well, I will say, so yes, we are able to simulate even when the vessel arrives early and idles. So we're doing a hour by hour cargo evolution, and the vessel just sitting there until some point in time in the future when the tanks are open, CTMS open. We can simulate the cargo continuing to develop, because sitting and idling really is just right. Your shaft speed is zero. Maybe your main engine consumption is zero. Your generators are consuming. And to give a little more flavor and context to that answer, like I said, we're doing an hour by hour evolution. We're considering really measuring the cargo tanks can be modeled with just well, the inflows and outflows of the cargo tanks are really what we're modeling. How much LNG, how much vapor is going to whatever consumer? How much condensate flow or subcooled LNG is being put back into the bottom? Now, if we simulate that the vessel gets to port early and arrives, then those outflows and inflows, they will change depending on which shaft speed are we going, how much reliquefaction is occurring. But we can continue to model that cargo into perpetuity. I believe under our belt, we have some very long voyages of, I'm thinking a month or 2 months or 3 months. Maybe it was a contango play or something like that. But yes, we do have experience modeling after arrival.
Yeah, I think after all the way to final consumption, it might mean when the gas is being consumed downstream. I think it might be what he said thank you. So I guess it looks like you got your. Yeah, very good. So Christopher Desser, who's president of Jonaro Technomar Services in the US, regarding terminal discharge, loading temperatures and pressures, some terminals like the ones here in Savannah are both receiving and exporting LNG. Is that something the model can consider? I mean, I guess you're just trying to get to whatever the terminal wants, I suppose, isn't it? It's you're not modeling the terminal itself, is it?
I'm not sure if I understand that question, but I'll answer it this way. We consider our entire simulation is you can consider from CTMS closed to CTMS open. Once we load the cargo, and with high frequency data coming from the vessel, we know the starting point of the cargo, we know the temperature, we know the pressure, we know the composition, and then we simulate all the way up until some point where like an ETA or CTMS open, where we say, okay, this is the final point when the arrival pressure and temperature will be levied, when they're being considered. I hope that answers your question. I'm not sure.
Yeah, but I guess modeling the terminal itself is something different, which you're not getting into, I suppose. We have to create our boundaries around. Yeah.
Yes, we're just considering the vessel. Yeah, nothing about. We're not modeling anything particular to loading or discharge, if that was the question.
Oh, very good. And who is actually doing this in the company? Is it? I mean, you talked about crew a lot, but this is quite hard for crew to do all this. I wouldn't have thought crew have this kind of expertise. So it's more the office staff, is it?
So we have the onboard, onshore teams using this tool for planning purposes, for charters, say making operational decisions like telling the crew, okay, utilize GCU, turn on your reliquefaction system. In the past, like I said, we were pushing recommendations to crew, but onboard crews, they they have all of the context and all of the expertise to come into this tool and input their set points and spit out results for what are my operational set points that I should be operating with. Or I'm a master before departure. I know that I'm going to or I plan on operating with this voyage plan. He can type all that in on the bridge if he has an internet connection and then see the outcomes associated with. So no, not limited to shoreside teams at all. Totally applicable for the onboard crew as well.
Yeah. Well, I would have thought the main benefit is this makes it easier to manage everything. People don't get surprises, and
Yes.
when you mentioned the $150,000 a year, I mean, I don't know how much an LNG vessel makes a year, but it sounds like peanuts to but it's the manageability is perhaps the bigger benefit to
Yes. How can we manage this asset better? How can we make better planning decisions before the voyage starts, before we've identified a discharge port and actual execution of the voyage? How can we operate the vessel best so that we're minimizing that consumption, delivering more at the end of the day?
Yeah. But the bit about the terminals. So the terminals ask for a higher pressure than the ship might be at. I wasn't sure if you meant the ship was a higher pressure than the terminal wants, or the ship.
Maybe I flipped that, but for a terminal might say come in at 12 kPa, for example. Your vapor header pressure needs to be below a set amount. And the vessel might be sailing around, coming into port at 18, 16, whatever, some higher vapor header pressure. Then the onus is on the ship to reduce the pressure in its tanks. Now, how can I do that? Several ways. We can burn the gas in GCU. We can speed up and pull more vapor off, put it into our engines. Often vessels will sail around in laps doing that outside of ports, which is, on paper, it sounds crazy, but we're trying to minimize those sorts of behaviors. How earlier in the voyage can we make better cargo conditionings? What's the word? How can we better plan cargo conditioning so that we can avoid GCU consumption, avoid having to sail around in laps?
Yeah, that's, I guess it counts as flaring gas combustion unit consumption, isn't it?
Exactly. How can we minimize that? How can we put all the LNG consumption we plan on to good use in the propulsion system? Or how should we best operate our reliquefaction system? Maybe we should start it early as opposed to later, or maybe because if there are very calm seas and our cargo condition is favorable, we won't have to use that reliquefaction system until later in the voyage. So a tool like this gives us, weeks out from arrival, the ability to see the impact of those cargo conditioning strategy decisions and plan better. And obviously, as we go along through the voyage, things change, right? The vessel might have a plan, but it might deviate from that plan, or the weather forecast might get updated. So I made the analog comparison to optimized weather routing. These simulation results can be optimized day over day over day, so that users are always dealing with the latest and greatest information and the best simulation results.
Oh, very good. So we've got a question here from Pierre Emmanuel de Sez, who's the Innovation Program Director at GTT. So I don't know if he's a competitor or a customer, or perhaps both, but he's asking, are you simulating the ballast passage as well? You haven't said anything about the ballast passage, so I'm guessing.
I haven't said anything about the ballast passages. So far, we've totally been focused on laden passages and getting them perfect and crystal clear. We have a lot of expertise simulating the total fuel consumption required for any leg. So that is the ballast as well. And knowing the total fuel consumption that's going to be required for an upcoming ballast leg, with that, we'd be able to predict the amount of fuel that we need to retain on board. But right now, we are not doing anything in terms of the cargo condition, temperature, and pressure prediction during those ballast passages. Right now, our focus is getting the entire lane segment nice and tight and exactly where we want it before we divert attention and start looking at ballast and fuel.
I think the ship has to arrive at a certain temperature and pressure after the ballast leg, isn't it, for loading? Isn't that right?
And in a bigger challenge of how do I want to cool down my tanks for loading? What are the best cool down strategies that we want to employ? That's a big question within the industry, and something that we're thinking about. But like I said, post laden.
Yeah, I mean, it's the same simulation engine, I guess. Sounds like a, yeah.
Though thermodynamically, they're very different environments, right?
Okay, right.
When you have the liquid dominated tank, right, up 95% full or whatever, and just a little bit of vapor compared to almost all vapor, it makes for thermodynamically it's a different modeling challenge.
Yeah, that's very good. How do you know how good your models are, by the way? I mean, I guess you talk about the physics, but I guess if you've got the insulation measurement slightly wrong, your calculation of the vaporization rate will be wrong, isn't it? So I
So
guess you have to check it.
accuracy for models is done via on-voyage and post-voyage comparisons. So at the beginning of a voyage, we can make a prediction, X will happen, and then we can compare that to results. Or like one of the key ways we talk about model accuracy is, say, vapor header pressure. We will predict vapor header pressure over the course of the voyage by feeding in the actual shaft speed, the actual consumption, the actual reliquefaction that occurred over the course of the voyage, and then look at our modeled value of vapor header pressure and compare that to the actual value. And doing that for all of our modeled features, pressure, temperature, speed over ground, consumption as a function of shaft speed, for example, we're able to identify for each feature how accurate is our model assessment. And that's what gives us the confidence to say, make recommendations or predictions 2 weeks out, 3 weeks out.
Yeah, it's great to hear her talk about real world simulation when we've been doing so much AI lately. So real world simulation, it gives you the right answer and you can see where it came from and know why it's doing it. And yeah, that's
for a second, I'd like to linger on that point of accuracy. One of the biggest barriers to adoption in this and other voyage optimization recommendation products is trust. Trust by the shoreside teams that these are accurate recommendations, but really trust by the crew that the things that they are being recommended are actionable, realistic, real life, especially when they differ a little bit from what they expect. How can they trust that the outcomes we are predicting are going to come to bear? Because at the end of the day, they're liable, right? They need to ensure that the ship gets to where it needs to be safely, that they're meeting their charter party requirements, terminal requirements. So this point of trust in the model results is paramount. Being able to demonstrate that accuracy clearly and, like I said, actionably, it's super important.
I guess it happens over time. If somebody says that the thing said it was going to be this pressure and it wasn't, that would soon kill the trust. But I guess over time, people realize it all works. And yeah. Yeah, that's very good. Well, we're coming to the end of the time now. I don't know if you want to leave any last words about so if you want customers to try it out, well, I guess we'll share your contact details to people after the end of the webinar. And
Yes, absolutely. Please, feel free to reach out to me. I'm happy to answer any questions, comments. Go to danelec.com if to learn a bit more about the simulation toolset. We're constantly enhancing this product. So much of the development has come from the industry, the users, right? So always very interested in your feedback and happy to take any more technical questions, commercial questions, anytime.
I've got one more question. This is Marco Stokov, Marine Advisor from GMS Global Maritime Services. We're all aware of charterers' role in cargo management. Have you seen weather routing information being a part of clauses in charter parties?
So weather routing, particular to boil-off, particularly the boil-off problem, particularly LNG carriers, we don't see a lot of great solutions out there in the industry where routes are being optimized considering the actual impact of sloshing, the resultant impact on pressure, and then the resultant impact on what cargo conditioning is going to be required at the end of the voyage. Danelec right now is diving into weather optimized routing. With our boil-off expertise that we have, we are in the future going to be tackling this problem. I won't say much more, but we're thinking about this hard right now and excited to dive into it because we don't see a lot of great solutions out there in the industry for weather routing, specifically for LNG carriers.
Yeah, I think so Marco's an LNG expert in Croatia, but I think what he's asking is, do you think charterers could require this? So saying, we want you to use this. We're going to charter. I think that's what he's saying.
I see. We've actually had we've had conversations in the past about exactly this. Clauses particular to simulation results. Yes, we absolutely think it was possible. We have some examples of those types of clauses based on our simulation results in the past, and we think it is the right direction to go. When the charters and the owners operators are collaborating across the same data sets, the same idea of performance, the same simulation results, that's where we're seeing alignment where we had misaligned incentives before. Where if an operator just wanted to, if all they had to do was meet the charter party requirements and the emission scores for the vessel were good, there's very little incentive for them to do much better so long as they're within the bounds of the charter party. So having these common simulation results and putting in clauses into the charter party to enhance that collaboration, I 100% agree. That is that would only be to everyone's benefit.
Yeah, so the charterer gets most of the benefit from this kind of software, perhaps, is it, rather than
for different use cases, in terms of maximizing delivery, right? The charter realizes the maximized LNG delivery at the end of the day. In terms of the emission scores and reducing total emissions over the course of the voyage, right? That's very much in the for owners. So depending on your use cases, right, we see different value.
Yeah, well, it's fantastic. Yeah, it's a great story about real-world physics simulation in shipping, and I'd like to see a lot more of this being used in shipping. I think it's going to make a great help. So, yeah, I guess so. Please get in touch with Connor if it's something you're interested in trying out. And thanks very much. That's a fascinating story for our first webinar of the year. So, cheers, and I shall pass back to Farah for the closing words.
Thank you all very much.
Oh.
Thank you to our guest speaker, Connor O'Sullivan, our sponsors, Danelec, and our audience. If you have missed our Q&A session, don't worry, as we'll be sending you contact details soon alongside a link of a recording of this webinar on our YouTube channel. Join us next week on the 21st of January for our digital ship webinar, Better Ways to Use Technologies to Improve Seafarer Training and Skill Development. Check it out on our website and book your tickets. See you soon.
Bye-bye. Thank you.